we have here a compressed ball, and it's being shot out. It's going to slide down the ramp, and then it's going to jump off of this ledge here, and it's going to hit the ground. Okay, so we're going to find a whole bunch of things. So here's a couple other things. The ball's on a smooth surface, so what does that mean? No friction, so we're not losing any energy due to friction. The other thing, we are not assuming the ball rolls down the ramp. We're going to assume the ball slides down the ramp. Okay, it needs to be able to slide down the ramp because in order for a ball to roll, there has to be some friction. Okay, so we have a spring is compressed a distance of 12 centimeters. What should we do to that? So we get 0.12 meters, and 675 grams is actually 0.675 kilograms. All right, so the first thing we want to find is the speed of the ball when it leaves the spring. So what's going to happen is the spring gets released, and it's going to set the ball in motion, right? So once the ball is not touching the spring, the ball's in motion, is the ball going to speed up? No. Why not? So from here to here, is the speed going to change? No. In order for speed to change, what has to happen? We need an applied force. Well, if the spring is no longer touching it, and if we don't have friction, then the velocity should stay the same by Newton's first law, right? An object in motion stays in motion unless we have that unbalanced force. So what we're going to do is this first section, I'm going to put a circle. I'm going to isolate this system right here. Okay? And I'm going to call this side A and this side B so that we know we're going from A to B. So if I want to find the speed of the ball when it leaves the spring, I'm going to draw a picture of A to B. So I have my spring, I have the ball, and the ball is going this way. So here's my A. My ball is going to end up here at B. So this is what my picture of my isolated system looks like. So yes, I have A and B on this, this maybe table or whatever this could be. I have A to B here, but I'm isolating just this part. Now this is important because by isolating the system, I know that this is going to be my initial energy and my final energy. But my first question then to you guys is there height here? There's not, because we are isolating the system. Okay, now if I was talking about this whole picture, then yes, definitely height as part of this. This does have potential energy. But when I'm looking at the energies involved to go from A to B, okay, the height is not going to add energy to the system in this part of the system. Okay, in the whole thing it will, but for this section of the problem it will not. So what do I have for my initial energy? I have the spring, okay? Now obviously we start at rest, so what do we not have initially? Right, we don't have any motion. All right, how about final, what do we have? Just motion, okay? Do we have any friction in here? No, we have a smooth surface for the whole problem, so we aren't going to worry about any conservative forces. Because there's non-conservative forces, that means by the conservation of energy, that the initial energy must be equal to the final energy. Initially, I have the spring, so I have elastic potential energy equals kinetic energy. So this is going to be 1/2 kx squared equals 1/2 m. I'm going to call this V final, quantity squared. And I'm looking for that final speed when it gets to that B position. So the halves cancel out. I'm going to divide by m and then take the square root. So the final velocity is the square root of kx squared over m. So this equals the square root. K is 225 Newton divided by meters. X, the compression we said was 0.12 meters. We're going to square that. And then divided by the mass is 0.675 kilograms. So if you plug all of that in, you should end up with 2.2 meters per second. Okay, so this is my final velocity, the velocity of B. All right, now the next part, we want to find the speed of the ball just before it leaves the edge of the table. Okay. So that means I'm here at B right now, and if I make this C, this is the edge before it leaves the table. So what I'm looking at now is this system. Okay, so I'm isolating the system in order that I can just solve for the speed of the ball right here. So what that looks like is this is B, and then this is at an angle here, and then we come to a flat surface. So my ball is right here, and it's going to come down, it's going to come over here, and this will be my initial energy and my final energy. And I want to go through then and ask my 3 questions here. Is there height? There is. Now, since there is height, what I'm going to take some time to do now is identify the zero line. Where is my zero potential energy line going to be? Yep, it's going to be right with C here. So this is my zero potential energy line, which makes this what? This is my delta Y, and then I heard somebody say this is 0.7 meters. That's correct, but let's take a look at Y. We come over here. The whole table here is 1.7 meters tall, right? And from the ground to C, that is 1 meter. So I'm looking for this distance right here. Okay, so that's going to be 1.7 minus 1. So this distance is going to be 0.7 meters. All right, so let's go back to my initial energy here. I have height. I've determined the height. What else do we have at B? We also have motion. Okay, so that ball's in motion because it is at the corner here. And so the spring shot the ball off. Next, final energy. What do we have there? Motion. What about height? Not for this isolated system. So I drew the whole system here. So there's no height. This is at the zero line. So if I were to plug in delta Y thinking, oh, you know what, maybe I do have height, then I would put in mg delta Y, but I would put 0 for delta Y and be like, oh, I guess that goes away. Okay, so if for some reason you accidentally put an equation in there, it should work out that you're putting in 0 for some variable so that you don't have to worry about it. Okay. So there's no friction in the problem, so we know the initial energy is equal to the final energy. Initial energy has height, so that's gravitational potential energy. It has motion, so that is going to be my initial kinetic energy. And then my final energy is motion, so that's my final kinetic energy. And then once you have this set up, now we can go ahead and put the equations we have memorized. Potential gravitational energy is mg delta Y. Kinetic energy is 1/2 mv initial squared, and then that equals 1/2 mv final squared. What cancels out? The masses. Okay, we're trying to find the speed of the ball at C. That's going to be v final, so I'm going to multiply everything by 2 to get rid of this 1/2, and then I'm going to take the square root, so v final equals the square root of 2g delta Y plus v initial squared. Okay, but what is the initial velocity up here? 2.2. So my initial velocity at B is equal to the final velocity at B from the piece before. So it equals the final velocity from part A. Okay? So this is the speed that the ball is moving initially, because that was my speed once I hit B here at the end of that spring and in motion. Okay, so this is 2.2. So we have the square root of 2 times 10 meters per second squared times times 0.7 or 0.7 meters plus 2.2 meters per second quantity squared. And when you plug all that in, you should get 4.3 meters per second. All right, next. Now we want to know the kinetic energy of the ball just before it hits the deck. So let's take a look at our picture. So here we are, we're at C right now, and we want to know the kinetic energy here. So it would be nice then just to make this. So we have, this is D here. So from C to D, that is our next isolated system. So I'm going to draw a picture of that. We have C here. The ball's right here at C. D is over here. And then the ball's going to move like this. Horrible picture of the ball movement, but I think you guys get the idea. All right. This is going to be my initial energy. What do I have? Height and motion. So height and motion. What is my zero potential energy line then? Yep, it's on the ground with D. So this is my zero gravitational potential energy line, which makes this distance, delta Y, equals 1 meter. Okay, we know that because it's given in the problem. Okay, so we have that. How about at D, what do we have? Just motion. So my final energy just has motion. Okay, again, no friction here, so conservation of energy. The initial energy equals the final energy. So I take a look at my my things. I have height, so that's gravitational potential energy plus kinetic energy initial equals kinetic energy final. This is what we want to find, is this final kinetic energy. All right, so all I need to do is solve for this first part here. So I come over, I get mg delta y plus 1/2 mv initial squared equals the kinetic energy I'm looking for. And we can just do a straight up plug and chug. So the kinetic energy equals mass of the ball was 0.675 kilograms. G is 10 meters per second squared. Delta Y was 1 meter plus 1/2 0.675 kilograms times the initial velocity. What is my initial velocity? 4.3. So my initial velocity is equal to the final velocity from part B. So this final velocity is the velocity at C. That's going to be my initial velocity because that's the beginning of my system now. So this is going to be 4.3 meters per second quantity squared. And therefore the kinetic energy is, I got 13 joules. Okay, and